feel the vibe.
What's up, guys? Welcome back to another instructional video, Algebra 2 instructional video here with Mr. Gaines as we continue our exploration of nonlinear systems of equations. In our previous videos, we have taken a look at solutions to nonlinear systems of equations and how to find those both algebraically and graphically. Let's go ahead and let's jump directly into some more examples of solving systems of nonlinear equations algebraically and graphically, as we took a look at problem 2G in your notes. So again, algebraically, we want to try to use the method of substitution as best as we can. So I'm going to go ahead and label my two equations as A and B. Again, if I'm going to merely focus on solving algebraically, I would already be at a point where I'm prepared to substitute because B has isolated the variable y. Now I am going to want to graph, so let me go ahead and just restructure A as well, and so that I get y by itself. So if I'm going to restructure or rewrite A, I would subtract x squared from both sides, so y squared equals negative x squared plus 16, and then square root both sides, so y equals plus or minus the square root of negative x squared plus 16. At this point, if I want to substitute y from A into y from B, it would essentially be setting the equations equal to one another. So x squared minus 4 equals plus or minus the square root of negative x squared plus 16. To remove the root, I'm going to square both sides. So remember, if I square a binomial, the result would be the square of the first term. The product, or twice the product of the two terms, so negative 4 times x times 2 would be negative 8x, plus the square of the second term. On the other side of the equation, squaring the root of that should be x squared plus 16 would just leave me negative x squared plus 16. Now, in order to solve this is quadratic. I want to get all of my terms to one side, set the equation equal to 0. So I would go ahead and add x squared to both sides. So I'd get 2x squared minus 8x, and then I would subtract 16 from both sides. So this would equal 0. The 16s would subtract out. Now I may notice that these two terms have a polynomial, or sorry, a GCF. That GCF would be 2x. So I can factor out 2x. I have two factors that multiply to give me 0, so I can set both factors equal to 0, and then solving them, x would be 0, and x would be 4. Now I can substitute both of these back into the equation for B. I'm going to do that on my calculator just to keep it, actually really we don't even need the calculator, but if you wanted to, you could substitute in 0, and you'd get 0 minus 4, so negative 4, so y would equal negative 4 in this case. If I substituted in 4, I'd get 4 minus 4, so y would equal 0 in this case. So now I have the two solutions, 0, negative 4, and 4, 0. Again, we've gone through how to check those on the graphing calculator, and so I'll allow you to check those on the graphing calculator by typing in the value, the restructured value for A, where y is by itself, and the equation for B, and viewing the intersections. Let's take a look at H, because H gives us a little bit more complicated of a setup here. Again, this one is prepared for substitution already. So I'm going to go ahead and do the substitution here and take a look at this algebraically, and then come back and rewrite to put it into the graph. So it doesn't matter if you rewrite first or second, we can find the algebraic solution straight away here. So I already have y isolated, so I'm going to substitute x minus 3 in for y on the equation A. And so that would leave me with x plus 3 quantity squared plus x minus 3 quantity squared equal to 8. Now in solving this, I'm going to need to expand those binomials that are being squared. And so this would be x squared plus 6x plus 9, again following our rules for squaring a binomial. The other one would be x squared minus 6x plus 9, and this would equal 8. Now I want to solve for this quadratic, so I need to make it equal to 0, and I'm going to, at the same time, I'm going to combine some terms. So x squared plus x squared is 2x squared. 6x minus 6x would be 0. I'd have 9 plus 9, which would give me 18, and that equals 8, and then I set that equal to 0. So 2x squared plus 10 equals 0. At this point, if you wanted to solve, we could divide everything by 2. We could factor out a 2 and divide by it. So x squared plus 5 equals 0. I could subtract 5 from both sides, so x squared equals negative 5. Then square root, I'd get x squared x equals plus or minus the root of negative 5, which we know would be plus or minus root 5i, which would be an imaginary solution, and so there are no real solutions at this point. So if we do get to imaginary units, we could find the value for x, which we did actually find the value for x here, and then substitute in and find a value for y. It would end up being negative 3 plus or minus root 5i, but we're not really interested in imaginary solutions at this point. We're just interested in finding the intersection of a graph of these two equations, and this circle and this line would not intersect, so we have no real solutions. So these are examples of algebraic solutions to problems. Now let's take a look at applications. The real goal for any system of equations is to be able to apply it in a scenario that would be useful outside of the classroom. So we have some examples. They or may not be exactly real-life examples, but it kind of gets you thinking about how we could apply nonlinear systems of equations. So problem number 3 says Sally's high school is planning their spring musical. The revenue R generated can be determined by the function R of t, where t represents the price of a ticket. The production cost C of the musical is represented by the function C of t. Sketch a graph of the two functions, then find the highest ticket price that can be charged without losing money on the event. So we have, again, two functions. Revenue and cost are our two functions. So revenue is R of t, cost is C of t. T, the function t, represents the ticket price. So I'm going to sketch a graph here. I want to label my axes. So this is going to be our x-axis. Our x-axis is going to be ticket price. And our y-axis is going to be either revenue or cost. This is going to be a dollar value. So I'm going to have two functions that I'm going to place on this. And I'm going to use my graphing technologies to help me out here. So I'm going to go to y equals. I'm going to clear out anything that's in there. Notice that I didn't draw the entire Cartesian plane here. I only drew quadrant 1. The reason I only drew quadrant 1 is because really ticket price is only going to be positive. I'm not going to have people pay me for, or I'm not going to pay people to take the tickets, so I'm only looking for positive. And revenue and cost can only be positive. We could never have negative cost. We could have negative revenue, but not negative cost. So let's do negative 33x squared plus 360x. This is going to be my revenue function. The first one that's going to be drawn is revenue. And then 700 plus 5t, that's going to be my second function. So we don't know what the ticket price is exactly. So let's go to window. And let's set x minimum to 0. The lowest price we'd have for a ticket is a free ticket, 0. And let's set x max to 10 for right now and see what happens there. So let's set x max to 10, and I'm going to hit zoom and go down to 0 or zoom fit and take a look at my graph. So the first curve here is the revenue curve. And the second curve there is cost. And this kind of gives me enough to answer the question. So I'm going to go ahead and sketch this in. So I went from 0 to 10 on the x-axis, and then I'm going to kind of sketch what I see here. So I have this parabolic curve. And I'm going to label this parabolic curve after I draw it in. So I'm going to sketch it kind of like what we have here. I'm going to label this parabolic curve as R of t. So this is revenue. And then I have this linear graph there, and I'm going to label this as C of t. This is cost. So it says sketch a graph of the two functions. Check, we've done that. Then find the highest ticket price that can be charged without losing money on the event. So my revenue is this parabolic curve here. My cost is this linear curve. In order to gain money, I would need revenue to be greater than cost. Now, eventually the revenue comes back and intersects the cost, and it intersects in two locations. It intersects over here on the left, and it intersects on the right. We're only really worried about the right intersection. Now, you could solve this equation graphically, if this system of equations, or sorry, algebraically if you wanted to. But because I have the graph, I can find the intersection of that graph, hitting second trace, going to intersection, and moving my cursor over. I want that intersection on the right, so I'm going to move it over close to that intersection on the right, hit enter, make sure it's on the second line, hit enter. I'm not going to need to guess, I'm just going to hit enter. So we're going to go ahead and round this. The ticket price is the x-axis, so 8.157, and I'll write it as 8.157 and come back to that in just a second. Then the y-axis would be 740.786, and I'll come back to that. So it says find the highest ticket price that can be charged without losing money on the event. So this point right here is 8.1571, and it goes on further. Let's talk about rounding this. Ticket price is the x-axis. Normally we'd want to round this to 8.16, but 8.16 would go past this intersection, and so revenue would be below cost. So we don't want to go past this intersection. We'd rather be just before it. So the highest ticket price would be $8.15 per ticket. So we can see here the intersection is the solution to the systems of equations. We just have to be careful there with rounding. If I go to $8.16, then revenue would be less than cost. So $8.15 would be the highest ticket price we could charge without losing money. Let's take a look at another example. Problem number 4 says a pelican flying in the air over water drops a crab from a height of 30 feet. The distance the crab is from the water as it falls can be represented by the function negative 16t squared plus 30. We might recognize that function from earlier this year, where t is in time in seconds. So to catch the crab as it falls, a gull falls along the path represented by the function g of t, which is negative 8t plus 15. Can the goal catch the crab before the crab hits the water? And sketch a graph to support our answer. So we want to know, is the gull going to catch the crab? So let me go ahead and let's graph this. So I'm going to clear out my previous equations. I'm going to type in my new equation. So the first equation, negative 16t squared or x squared plus 30 represents the crab. My second equation, negative 8t or negative 8x plus 15 represents the gull. I'm going to go ahead and leave my window from 0 to 10 on the X for right now. I'm going to hit zoom and go down to zoom fit to see if I get a good picture of this. And that's kind of a lot more than I need. I don't need negative height here. So I'm going to reduce my window. I'm going to go from 0 to, let's say, 4, and then zoom fit. This is a lot better, still a lot more negative than I need, but now I'll just adjust my window to go to a Y minimum of 0, and that's good enough, okay? So your graph may look slightly different depending on what your Y maximum and Y minimum is, or your X max and X minimum. So on the X axis, I went out to 4. Remember, X is our T, which is time, and this is in seconds. The y-axis is height. So height of the goal is represented by g of t. Height of the crab is represented by h of t. And this is in feet. So I'm going to sketch in my two curves. So this one is my parabolic curve here is the crab. So we're going to call this h of t as it was represented in the equation. And my linear line here, let me move where h of t is at, just so we know which one it represents, h of t. And my linear equation here is g of t, which is the goal. So it says, can the goal catch the crab before the crab hits the water? Well, the water would be at a height of 0, and so we can see that there is an intersection. We could find that intersection if we wanted to. And that intersection would be at approximately 1.255. So the answer here would just be yes. If we wanted to go further, we could say that the goal will catch the crab 5 feet above the water. Or we could say that the goal will catch the crab 1.25 seconds after it begins to fall. So the question really just asks, would it be able to catch it? The answer is yes, because there is an intersection. If we wanted to go into some of the logistics, it would take the goal 1.25 seconds to get there, and it would catch the crab 5 feet above the water. And there we have a solution for our system of equations. Problem number 5 gets a little bit more involved. It says the price of stock AX over a 12-month period decreased and then increased according to the equation A of X, which is listed, where X is the number of months. The price of another stock, B of X, increased according to the equation B of X over the same 12-month period. Sketch a graph of both equations. State all prices when both stock values were the same. When did this happen? So again, we're going to sketch out a graph. We know that the x-axis is months, so we're probably going to start at 0 and go probably out. It does say over a 12-month period, so we're going to go out through 12 months. We know that the y-axis is the value of the stock. It does not say exactly what the value is in, so we don't know what the price is or the value is in units, so we'll just call it value for right now. Again, we're going to graph both of these two equations. So 0.75x squared minus 6x plus 20 and 2.75x, let me fix that, 2.75x plus 1.5 or 1.50. And I'm going to go in my window from 0 to 12. And then I'm going to hit zoom, and I'm going to go to 0, zoom fit. And I'm going to graph this. So this does not show my y-axis here. I'm going to go ahead and drop this down a little bit to see my y-axis, just because I sketched my graph out that way. So I just want to make sure I get this in that kind of format. So we're going to sketch this out. Again, it is important to not only just represent the picture, and it doesn't have to be a perfect representation of the picture, but to include labels. Include labels for your axes. When you have more than one equation, include labels for your equations. So A of X would be the parabolic curve here. B of X would be my linear curve. And again, we're not looking for exact drawing here, but just a good representation. Now it says state all prices where both stock values were the same. So we want to find the intersections. The intersections would be the case in which the value is the same. So I want to make sure I find my first intersection over here on the left. So I'm moving that cursor close to the left as I use the intersection function on my calculator. I'm going to round this one, 2.77 and 9.13. Now here there's no consequence. If we look at the problem, there's no need to round a certain direction like there was on the first application problem. So we're just going to round using the math logic that 5 or anything else is rounded up. So I found the second intersection. I needed to move my cursor over there this time. And it would be 8.89 and 25.96, about 25.96. So it says state all prices when both stock values were the same. So both values were the same at approximately $9.13 and $25.96. We're assuming maybe per share, but we're just going to leave it as that. This, and then it also says, when did this happen? This occurred during, it says over a 12-month period, but we don't know for sure if this is January to December. So this occurred during the 2nd and 8 months, respectively. So we've actually really done a considerable amount of work with finding intersection points graphically and using those to answer equations already this year. And so this is kind of just an extension of that process. So if we have nonlinear systems and they are in applications, we are able to graph those, find the intersections, and then put the value of those points back into context. You could potentially also solve this problem graphically if you'd want to, but, or sorry, algebraically if you wanted to, but graphically in this sense makes the work a little less difficult. And this is a good place to stop. So at this point we have concluded the SE.3 notes, taking a look at nonlinear systems of equations. As always, thank you guys for tuning in, and I'll